Hi, everyone, and welcome to Computer Vision today. So, we're now recording the lecture part. Before, we just sat together with Cronus for a while and had the Q&A about the challenge and discussed some of your questions. We didn't record this because otherwise some students may not ask their questions. And today we'll finish the lecture part of the course, and I'll say more about the organization as well. So, in the last week, or in the last lecture, not last week, but a bit back before the before we started with the Cronus Challenge and the project proposals, we finished the Kalman filter. We looked into the correspondence problem as well as the optical flow, and then finished the image sequence processing chapter. There was only one minor part at the end of the last lecture that I had a link to some concrete optical flow algorithms, and that URL did not exist anymore. You can either look it up through some internet archive, or I found a different one that I had also sent in iLearn to you. This is one example where you can see different optical flow algorithms and the kind of assumptions they make to ultimately make that equation solvable. I had shared this with you. Feel free to look it up. This comes from a library here. It's not to advertise the library, but they simply show a couple of concrete optical flow algorithms and the assumptions they make. So I found this example here quite helpful. Then we did not, or we're not teaching the foundation of mobile robotics chapter this year, but some students, they work on mobile robots for their project. So they have already watched the recordings from last year of that chapter. Since this year, due to this big challenge, our schedule is a little bit different. There's one chapter left in here about selected topics, and every year we discuss some of these topics. In addition, so you may wonder, how are we continuing after today's lecture? So you have your project proposals later in June, and today we have the last lecture part. So then you have even more time to work on your projects. So we're not meeting here weekly, regularly online. However, if you have any questions in the coming weeks, just get in touch and I'll be happy to help. And we can schedule an appointment either for that slot on Thursday or some other time during my office hours. And we will also have probably two more guest lectures this term. Concretely, we will have a guest lecture on May 28th. This one will be taught by Wolfgang Reuter. Wolfgang Reuter is a well-known data science expert in Germany, very active in consulting, and he has spent a lot of his private time on building AI systems to classify paintings into real or fraud, because there's a huge business around fraudulent paintings and yeah, so fake paintings. And he built an AI and has worked on this for many years in his free time to make sort of a prediction whether a painting is really by a specific artist or not, by a specific painter. Very interesting AI. He'll talk about this on May 28th, most likely. I hope we are able to do this on campus, but this will depend a little bit on Wolfgang's schedule. I will inform you probably a week or so in advance, and if it takes place on campus, you should attend on campus. If it takes place online, I would expect all of you anyway to attend online live so we can have a good discussion. And there will be with another company, possibly a guest lecture on June the 11th, but that's also still to be sorted out, whether it takes place, whether it takes place online or on campus. All of this we will see later. And these two industry talks, they would help you to learn a little bit about what people are doing. Plus, they are also looking for new staff. or new talents, and many of you are looking for an internship for next semester, or a working student position, or a full-time position after your graduation, or a spot where you can do your thesis. So that's why I want to connect you with industry partners. And so you should take advantage of these guest lectures. So what are we doing today in the last lecture part? In this selected topics chapter, there are various topics, and I don't teach all of them every year. And last year, we focused more on vision transformers and self-supervised learning, and because these two topics were also of interest to quite a few of the projects last year. This year, not too much because we have less individual projects because most students are on the Cronus Challenge. And this year, there are two topics that I want to focus on that are new to this course, which are biases in data sets and uncertainty in learning. And we'll come to them in a moment. There is one topic, I won't teach it this year, but that's the so-called generative adversarial networks. And generative adversarial networks, they could be used also for data augmentation or to generate potentially more training material. And you've just heard when we sat together with Cronus, they recommend also doing augmentations. So augmentations would be to increase your training data by taking the training data you've already got, you make some changes to it, add some noise, some rotations, or some other stuff, or add some artifacts. And generative adversarial networks could be an approach too to generate more training data. So you may be interested in looking into this. We recorded it last year, but this year we're looking in biases in data sets and uncertainty in learning. And both of these subchapters will help you to build better, more reliable vision systems. And these topics are actually highly generic and they can be applied to so many other machine learning problems too, not just to vision. And they are new this year in this course because I taught these two topics before in the big data course. So most of you are currently in the fourth semester, and in the sixth semester, there's a big data course. And I taught it until last year, but I'm no longer teaching the big data course because I got too many courses. Yet I found these two topics here very important, so I moved them into the computer vision course, and they will help you to build better, more reliable vision systems that can be helpful for your regular projects, and it can be helpful for you to perform better in the Cronus challenge. So I'm just quickly moving through to start with biases in data sets. If you are curious about the other selected topics, you can watch last year's recordings, for example, or from the year before. Next year, there will be some new selected topics because I also need some variation in this course and look into some new stuff. So we'll look into biases, and I want to know if you have come across the issue of biases in training data in the past. If this is something you have come across before, maybe you would just send a thumbs up or a green sticker. If you have never come across this and you don't know what a bias is in the training data, maybe send some other reaction. And at least two students have sent such a response, that now quite a few. So maybe you can tell us what kind of biases in machine learning you have come across. You can either use your chat here, or um, you can turn on your mic and tell us what the issue of biases in machine learning means to you. So I'll just wait a moment before I'll tell you my view on that. And you're anytime welcome just to turn on your mic and tell us so you don't
Um,
type all of this. Yes, hi.
so I had a project where I had to categorize good and bad pictures,
Hmm.
and I had about 36 bad ones and about 3,000 good ones.
Okay.
I solved it using oversampling. Yeah.
Okay. Can you tell us what oversampling is?
Basically, you just take the bad pictures and give it to the AI more often or to your model, so it can't just guess the picture is good and get a good score. So it actually needs to try and learn what bad pictures looks like.
Hmm. Okay. Yeah, interesting. And anyone else who has made such observations wants to share this with us?
Yeah. Uh, Also, a year ago, I was working at the company, real estate company, and I was making the tool for predicting the price of the apartment based on the a lot of parameters and images. And it was apartments in Athens. There was a big data set, like the governmental data set, and there was a lot of middle price apartments, and there was also a lot of over like super expensive ones, like for millions of euros. And those for the millions of euros, I usually were getting like under predicted because the data set was biased towards the middle middle prices, and it was really hard to teach the model how to distinguish million euro apartment from the middle one, because
Yeah.
yeah, it was really biased towards the middle price.
Yeah. Well, thank you very much for sharing all of this. And so in practice, most data sets are biased. And what does that mean? Obviously, we want our test data to be different to the training data because we train on a training set and then we want to test it on data we have not seen before. That's normal. However, it may happen in reality that our test data is not just different to the training data, but comes from a different distribution. So that the training and test data, they would be from different distributions. And that leads to lots of problems. And we'll look into this now and we'll see some consequences to vision, but also to other problems. So I came across this topic when I did my master's, but mainly during my PhD time, because even during when I did a master's in machine learning more than 10 years ago, a lot of professors did not really talk about biases in data sets. And still today, I feel a lot of machine learning books, a lot of machine learning courses, they teach you how to train models, but they don't teach you too much on how to address biases and make your models more reliable. Now, the term bias may mean actually a lot of different stuff in machine learning. And we first look at various different things, what a bias could be, and then we'll look at this issue here, that the distributions of the training and test sets are different. So the term bias, and this summary here, there may be more things that are called bias, but at least that's what was sort of most obvious to me. So machine learning models, they have an inductive bias, and this is some set of assumptions that they make. For example, if you use like logistic regression, you would assume that the training data is linearly separable. Or if you use linear regression, we would sort of assume these linear relationships in the data. Or if we use some Bayesian model, we would make other assumptions about the probabilities. So a machine learning model always makes some underlying assumptions, and that's often called the inductive bias. Then sometimes in the literature, the term bias is also used to describe underfitting. when you have this bias variance trade-off. Bias often means underfitting and variance means overfitting. So again, something totally different. And then another thing that is sometimes called a bias is if you have a hypothesis like this one here, H, where we have an input X, a vector X, and where we generate an output from that. So we take input X1, multiplied with our weight 1 from the model, and we do this up to weight n and element xn in that vector because it's a vector. So in bold, we have multiple elements, x1 through xn, but we also have our entry w0, which is multiplied by 1. So we could either say x0 is 1, or we just leave x0 out and we say our w0 plus this product up to this product. We would also sometimes call this parameter w0 the bias, because say in linear regression, we would call this the y-intercept. So by how much we move the hypothesis around by a fixed offset. So sometimes this here is also called a bias or a bias weight, for example. If you, for example, look into neural networks, you have a lot of these bias weights as well. So who of you has seen all of these three things before? The inductive bias, bias as a synonym for underfitting, or for this y-intercept. If you have ever seen all three together, or if you have seen all of them before in some context, maybe thumbs up. If there's at least one of these terms you have never seen, maybe send a thumbs down so I can just see who has seen most of this before and who has not. Largely thumbs down. But someone has seen all of this. So, but underfitting, well-known concept. You often have seen such a parameter W0 as the y-intercept. So even in a simple linear function, just with one parameter, you would have, or with one input, you have two parameters, one for the slope and one for the y-intercept. Or the inductive bias is simply the underlying assumptions that your model makes. Now, the third thing that can be a bias is this one here, that our data set or our test set comes from a different distribution than the training set. This is what we are referring to now when we talk about biases. So that's the bias in the context of this chapter. So that the distributions of the training set and test set are different. Obviously, the training set and the test set are different. That's required. But this time, the distributions of these two sets are different. Now, there are various consequences of this. So if we make conclusions from a biased data, so biased here could also mean that the training data is not representative, so that we have unrepresentative data and we make conclusions for that. Some of these conclusions may just be wrong. We may not be able to reproduce some of these conclusions, and we may not be able to generalize well. This is, however, an issue not just in machine learning. I think it's an overall issue in statistics and in research as a whole. Maybe some 15 years ago or 20 years ago, there was even a paper that claimed that most research published is actually wrong. So not just in AI in general, because the kind of data that is used for the research is not representative. And in machine learning, there are consequences of that. Say, if your training data is not representative and you make predictions, you could discriminate against certain subjects. For example, of underrepresented categories, you could discriminate against people because of their race or sex or whatever, simply because they are underrepresented in the training data, and then you make biased predictions. So this can happen. And today we will see how this can happen and how we can maybe address it. And we will first see that the issue of biases in data goes back to much earlier in statistics, so long before we started doing machine learning. So I'll show you a very famous example from how biased data sets can lead to chaos. It's concretely from the 1936 US presidential election. Does anyone know this example? If so, maybe just raise your like a thumbs up if you have never heard about the issue of the prediction in 1936, you would send your thumbs down. But if you have ever heard about this example, maybe send a thumbs down. So long ago, but an issue in statistics, and I want to talk about it. So nowadays, it's common that elections are sort of, there's a prediction who would win the election. And this is nothing new. This was done already in the 20th century for many years, and goes back to probably at least the early 20th century. So in 1936, there was the US presidential election, and the Democratic candidate was Franklin D. Roosevelt. He was elected president in 1932 and ran for a second term in 36. And his challenger from the Republican Party was Alfred Landon, the governor of Kansas. And so that was the election. And then people were curious who would win the election. So there were predictions in the newspaper. And there was a very famous newspaper at that time in the US, the Literary Digest. It was a general interest weekly magazine, and they had correctly predicted the outcomes of the elections in 1916, 20, 24, 28, and 32 based on straw polls. So in 36, they wanted to predict again. So they sent out 10 million questionnaires in order to predict the outcome of the presidential election. So that was long before we had large scale computers and all of this. So sending out 10 million questionnaires to potential voters was a lot of work. And they actually received 2.3 million returns. And they predicted that Alfred Landon would win massively. However, probably none of you have heard about Alfred Landon before. I also only heard about that guy the first time, maybe some 15 years ago when I came across this story. So they predicted, despite 2.3 million returns, that Landon would win. But Landon obviously did not win, and Roosevelt was elected. And finally, he was not just elected to a second, but a third, and then even a fourth term. And this was the outcome in 36. So PLU stands for Roosevelt, the Democrat candidate. And you see he won almost all the states. And Landon, here in red, did not win very well. He even did not win in Kansas, his home state, by the way. So the question is, they sent out 10 million questionnaires, and how could this go wrong despite the 2.3 million participants? So this was really big data at that time. Are you sort of, if you feel surprised that this went wrong despite 2.3 million participants, maybe send some reaction or something, because I already saw some surprised reactions here in the chat. So this was really big data, and it still went wrong despite the big data. So how could this go wrong? And I think the key question is here, where did they get those 10 million addresses from in 1936? And they double and triple checked that they counted correctly. So they didn't count wrong. They really properly assessed the results manually or the returns that they got. So they didn't do that one wrong. Now the interesting question is, where did they get 10 million addresses from in 1936? It turns out those 10 million recipients, they mainly collected their addresses from car registrations and phone directories. And remember, this was 90 years ago. And in that time in the US, only disproportionately rich people had a car or phone, and most people probably did not have a car and did not have a phone. So they were not in these car and phone directory or car registrations and phone directories. So what we see here is they drew from a heavily biased part of the population, of the overall population, because most people did not have a phone and most people did not have a car. And those disproportionately rich people, they tended to favor Landon, the Republican candidate, over Roosevelt. So what in fact happened here is they had a heavily biased data set. Maybe just confirm if this sort of makes sense to you, that in like 90 years ago, most people did not have a car and did not have a phone. So, because also here, like in Germany, at least in West Germany, I think most people still didn't have a phone at home in the 60s, from stories that I hear from my grandma, that a lot of people only had their private phone line maybe in the late 60s, early 70s, even in West Germany. So not speaking about East Germany, obviously, which was probably way more behind in that time. So in 36, yeah, also in the US, most people did not have a phone and did not have a car. And so this caused a big problem. And it was also shown later, they had sent out 10 million questionnaires and they got these 2.3 million returns. And it was shown even later that there was another bias, that those who favored Landon were more likely to respond than those who did favor Roosevelt. So that created a second bias, surprisingly. But the main bias obviously came from how they collected the 10 million addresses. So we see big data is not necessarily the solution. And in sometimes maybe when you look in polls and predictions of elections, maybe you heard about so-called Gallup polls. That's a term used widely in election predictions. And George Gallup, he was active in 36 as well, and he only interviewed 3,000 people that he handpicked because he aimed to create a largely unbiased sample of the population. Probably you're never 100% unbiased, but very low bias sample of the population. So he handpicked 3,000 people, interviewed them, and Gallup actually could predict the outcome of the election very well. So 3,000 responses worked far better than these 10 million questionnaires and 2.3 million returns. So that's something quite interesting. So you see that having big data is not necessarily the solution. You would rather have smaller data sets that are more representative. This can help far more than an ever bigger data set. So I remember some 10 or 15 years ago, a lot of people started talking about big data and said the more data, the better. Sometimes more data is helpful, but rather we have more representative data, and we can use this more representative data and do maybe some augmentation on it, and then create more data than just randomly drawing more data. Because if we just collect more and more bias data or low quality data, because there's not just the bias, you may also have lots of errors in the data, incomplete data, that will not help. So don't just aim for more data, aim for more representative data. And what happened in 36 very quickly killed the Literary Digest because people had really trusted that magazine because they had correctly predicted in 1916, 20, 24, 28, and 32. And then they failed in 36. And this weekly magazine had then disappeared relatively quickly because the customers lost trust in it. This issue that predictions of elections went wrong happened many more times, obviously. For example, here in 48, Truman was the US president and he ran for a second term. And there was here the Chicago Daily Tribune, and they had made their own prediction during the election night and already printed the newspaper that Truman would be defeated, or that Truman was defeated by his challenger. And then next morning, when the newspaper came out and more results had come in, the Chicago Daily Tribune was actually wrong, yet they had already started selling their newspaper, the daily edition. And here you can see Truman, who is laughing because he won, but the newspaper had made the wrong prediction during the election night. So very famous photo from 48 as well. And you've seen this in 2016, so 10 years ago, that almost all the media outlets had made their predictions and they were so certain that Hillary Clinton would be elected president and that Trump would lose, yet Donald Trump won the election in 2016. And because again, for these wrong predictions, oftentimes heavily biased data was used, and maybe sometimes newspapers also wanted to predict something or predicted something they wanted to predict. That's probably sometimes also part of the issue, but the data was biased. And there were still a few outlets that predicted 2016 properly because they paid more attention to data quality and bias. So you see this issue keeps appearing over and over. What happened here in 36, it turns out this was not fully understood in 36. So statisticians, so researchers in statistics, they only started to fully understand the issue of bias in this data set in the 70s. So it took like 35 to 40 years for research to fully understand what went wrong in 36. So you see, it's a long-standing issue in statistics. And obviously, since it's an issue in statistics, it's an issue in machine learning. And now we'll come to the machine learning part where biases play a role. So I'm now only interested in a supervised learning setting. So we have training examples where X is our input, X is a vector, so multi-value or can be an image or whatever. But doesn't matter whether it's an image or just some data, that's why in bold. And it has index I, and in my notation, you've seen this notation before, I always prefer to use an superscript index for the enumeration. So I have input xi and the label yi, and the label is just one label, that's why it's not in bold. And we have our training examples, and we draw them from a training distribution. So we have a training distribution for X and Y, where capital bold X denotes the data and a bold capital Y denotes the labels. And this training data comes from a training distribution. And later we will have test data that comes from some test distribution. And if these two distributions, so the training distribution and the test distribution are different, then we have a bias. So we could try to correct for this bias. But we will see very soon there is not just one type of bias, there can be many types of biases in the data. So this here sort of makes intuitively sense. The distribution for the training data is different to the test distribution or the distribution of the test data. And now we want to correct for this. And the literature recommends something. And what it recommends is the following. It says we can reduce a bias. And for this is we take some example, xi, yi, and when we train a model, we could assign a certain weight to it. I know many of you use libraries like scikit-learn or something. Have you ever seen in scikit-learn that for some models you can not just pass your training data, but also weights for the training data? Have you ever seen this? If so, maybe thumbs up or thumbs down. So some have seen this. Perfect. Not with all models, but with some models, you can pass weighted samples. I'm just briefly in parallel looking for an example, and I will screen share this now. So I've just found an example spontaneously in scikit-learn. That's just that first one I found. So we have a support vector machine, which is one of many models in scikit-learn. And what you see down here is when you fit the model, then you can pass not just your X and Y, so not just your training data or your input data and your labels, but so X would typically be a matrix because you have rows of examples and your examples is a row, multiple entries, and Y is a vector of all the labels. And then you can also pass another vector, which are the sample weights. And this parameter is called sample weight, and you would have some weight. So you would have one weight per example that you can pass. So some of you raised their hands that you had seen something like this before in, for example, scikit-learn or some other library. So you can say some examples are more important than others when training the model. And you can do this for other models in scikit-learn as well, not just for this SVM. Not for all of them, but for some. So we could say, well, we can reweight and assign a weight to our examples when training based on how representative they are. Whether they should be considered more when training or considered less based on their relevance. And the literature proposes I can calculate like a vector W, which are the weights, and the concrete ith entry would be for the ith example and its label that we could see what's the probability of that pair, so the input data and the label appearing in the test distribution, divided by the probability of this appearing in the training distribution. And then we can calculate the weight, and we have a weight and say this is the weight of how important the example is. And like this, we could try to mitigate a bias by considering an example more or less. Now, we can do this, but in practice, calculating the weight like this does not work very well. It's actually highly impractical in many cases because in machine learning, we have the curse of dimensionality. Who of you has heard this term before, curse of dimensionality? It's definitely something that should have been mentioned in your machine learning course. Maybe some more thumbs up because there are not that many yet. Because X may be many dimensions, plus we have a label, and we would need a lot of these combinations in our training data. However, if we have high dimensional data, we just typically by far don't have enough data to have enough data spread out in that space because of the curse of dimensionality. So calculating these probabilities here or estimating them well does not work very well because I have my data, but oftentimes I have limited test and training data, and I would need to approximate the distributions. And approximating distributions, there are algorithms for this, but it's very slow and doesn't work very well if I have very limited data. And typically, I just have by far not enough data to do that. And I would need to approximate the distributions to then calculate these probabilities. So that doesn't work very well. So while calculating the weight like this in theory may work, in practice it does not work, especially because X may be high dimensional, plus I need a combination with the label in that space. And I may have not just binary labels, but a lot of different possible classes. So it turns out we need to make some assumption about the exact bias we are addressing. And if we make that assumption, then we can calculate this weight probably much faster and we can approximate it much better. And there are now two types of biases that I want to discuss with you. One type of bias is the so-called class imbalance. And the class imbalance is something I think from the explanations we heard before from some of the students, something some of them have come across before. So class imbalance means, say, we have a binary problem, and I have a training set, and my labels are unequally represented. Say I have 10,000 training examples and maybe 9,000 training examples from the one class and 1,000 from the other. If I have this, I have a biased data set. Concretely, I have a class imbalance because I have more examples from the one class than the other. And I will introduce class imbalance now from this framework that we have here, that we look at these distributions, and then we are making some assumptions. And when we make these assumptions, it will turn out that we can calculate this weight much easier. For class imbalance, what we will assume is that the distribution for the labels, so we have a training distribution for the labels and a training distribution for the test, that these two distributions are different. But however, we assume that we also have two conditional probability distributions where we have the training distribution of the data given the label, and that one is the same as the test distribution for the data given the label. We assume the first one is an inequality, the second one is an equality. It's just an assumption we make so we can calculate this weight easier. Class imbalance could be, for example, visualized like this, that I have much more examples of the one class than the other. But here in particular, we assume that these label distributions, they differ between the training and the test. Now you may wonder, why have we made that assumption? I will show you this now on the whiteboard because we can then much easier calculate these weights from before. So I'm just opening my iPad. And there we go. So biases in data sets. And we'll look at the class imbalance. So, and for class imbalance, we have made the assumptions I had just shown you in the slides, but I'll write them down here again. So the distribution for the training distributions for the labels. So Y is in bold. That's different to the test label distributions. But we've assumed as well that we had these conditional distributions. So for the training, the data given the label, we said that's the same as for the test data where we have the data given the labels. And we've worked a lot with conditional probabilities before in this course, especially when we looked at image sequences. So conditional probabilities you should all be fine now with. And then when we have made this assumption, we can in fact do something quite interesting. Before we said we calculate our weight I by looking at the probability of our data, or a concrete example, xi, and its corresponding label. We set the probability of disappearing in the test distribution divided of disappearing the training distribution. We would calculate our weight, but we said calculating this is not very practical, but we have made this assumption for the class imbalance. And what we have down here, because we have this comma, is we have, well, I'll just put this in. Here we have this joint probability distribution concretely of the data and the label. But you all know conditional probabilities. And just as a side note, so I put a side note here. If you say I have a probability of x and y, I can re-express this of p of x given y times p of y. Who remembers this law of probability theory, that I break the joint probability into a conditional probability and a prior? If you remember this, maybe thumbs up. We've seen this quite a few times in this course now. You should have seen it in other courses. So this is a law of probability theory, and we can apply this now over here by taking this inequality and that equality. So we can say, well, we can say that this is P of test of xi given yi times P of yi. And we also test. And we can do the same, not just for the numerator, but also for the denominator. So P train of xi given yi times P of train, or P train of yi. So we have just applied this probability law to break this joint probability into a conditional as well as a prior. And now we assumed in here that these conditionals, so x given y, for train and test are the same. And this would allow us to cross out these two here because we assume they are the same. So we can extremely simplify the calculation of the weight by just calculating p test of yi, and we take this and divide it by p train of yi. Do you see how this probability law can help us to calculate the weight more practical? If you understand this derivation I've just made, maybe thumbs up. Because all I have done before was an assumption. So this in blue up here is my assumption. And I have said this is what a class imbalance would look like, that the distribution of the labels differ, but not the data given the label. And then I can calculate this weight much easier than before. And that's exactly what I have done here. So I have just shown you this before, and now I have derived this here on the whiteboard. And now we have a weight, and I can pass this weight when training um, a model. I can do other things like undersampling or oversampling. These terms were also mentioned by at least one of the students before. So oversampling would mean I take the minority class, so the smaller class, and I would duplicate some of these examples to create more examples of the underrepresented class. That would be oversampling. I can do an undersampling as well, that I would delete randomly some examples of the majority class, but that would come with some loss of data. While with oversampling, I would recreate some examples of the minority class. There are techniques combining this, like SMOOTIE, which stands for Synthetic Minority Oversampling Technique. That's something that was quite famous until a while back, and the idea is we would oversample, but we would not just copy examples, but we would try to find some pattern in the minority class in order to have more authentic examples rather than just copying from the minority class. And then we would massively oversample, but then we would undersample the whole data set to keep its size manageable. This is something that was published in the literature maybe 20 years ago or so. But in recent years, there have been some arguments that SMOOTIE wouldn't really work, and a lot of people have not been very satisfied with it. But I think there are still some practical use cases when this works, but maybe not for every possible data set. But that's something we see often, that techniques don't work suddenly magically for every data set, because SMOOTIE itself makes some assumptions. And these assumptions, they hold true for certain data sets while not for others. So this SMOOTIE was used a lot, but recently, I think in the last few years, there has been a discussion whether it's so useful or not, but maybe for your problems, it could be helpful or not. But you can do undersampling, oversampling, you can calculate the weight like this. The weight can be used for under and oversampling. You can use this weight for the training. So there are lots of different techniques. And for the Cronus challenge, this may be helpful too, because maybe one class is heavily underrepresented and in your training data, and maybe in your test data, the distribution is different. So maybe one class that is underrepresented, you could, through augmentation, create more examples, and then maybe have a distribution that fits better your test data. How to handle the imbalance exactly? I think there's not this ultimate recipe, because sometimes you will simply, in reality, not fully get rid of the class imbalance. And it's okay, because so you don't need to augment your training data in a way that it has an even amount of examples in both classes. Because later, when you test it and the distribution in the testing is different, well, then your learner would be focused too much on a class balance rather than an imbalance. And if you, for example, have, say, an anomaly detection problem, yes, probably most examples that you're looking at, they are not anomalies. Most examples are okay. And if you take your training data and you just try to create a class balance, maybe you would make a lot of wrong predictions on the test data. So the ratio you would train on should rather be the ratio that you would have in your test data. So if you know more about your test data, that's helpful. But sometimes you also don't know that, and you need to make some predictions or some assumptions. Sometimes you may want to take your training data and create a perfect class balance. So there's not this one recipe. It depends a bit about how much you know about your data and the setting. But it's certainly something you should investigate now for the Cronus Challenge as well as the other projects that you're doing, because if you understand the issue of class balance or imbalance, maybe you can build a better classifier than before, or a better regressor, or a better whatever model. So, well, for regression, the class imbalance problem doesn't exist because it's obviously for classifiers. But in, say, regressions, you can have the issue too that maybe your label values are somehow spread out in an interval, and you would sort of have a somewhat imbalance that maybe most of your labels would be in one end of the interval and they wouldn't be spread out well. This is obviously not called an imbalance. There are different terms for this, but I think it was also mentioned in one of the discussions. But it's something you also need to look at when you build a regressor, how your labels are spread out and how you could maybe fix this. But we've now looked at this for the class imbalance. So it would address your classifier. And a lot of you have picked classification problems also for the regular projects. The Cronus challenge is about classification. So look into this. Maybe it will help you to build a better classifier. And there are real world consequences if you build this wrong. So this was from a Google app or a feature in Google Photos, maybe some 15 years ago or so. What happened was you could upload your images in Google Photos and your images got automatically classified by an AI. Where do you see a problem in this set of examples here? Where could the label be extremely wrong? If you see it, send it to the chat, please, because we have these sample images plus a label that Google Photos generated. What do you think went wrong? Which of those examples? I saw a dead skull sticker here in Zoom. Yeah, the problem, the skyscraper, airplanes, cars, bikes went fine, but the problem is this example here: people of color who got classified as gorillas. And when this came out some 15 years ago, Google was in hot waters and they faced obviously a lot of criticism about racism and so forth. And what went wrong was the training data. And that's a general issue, I think, about training data about humans. Most training data in data sets is about white men. There's not that much training data about women, and there's not that much training data about people of color and other races, obviously. And the data set that was used here by Google was mainly probably had white people with a human label. And then there were obviously gorillas and other animals. And once you started classifying people of color, the AI may have classified them as gorillas rather than human. Not because the AI was built by racists, but rather because a lack of representative training data. Has any one of you ever heard about this example here or a similar one that an AI caused a lot of discussions after such a classification? So, yeah, someone has heard about this. So this led to a lot of trouble. Google claimed they fixed it very, very quickly within a few hours, which I don't think they fixed it personally. What I think is they just disabled that they to predict gorilla labels and similar labels. I think they just turned this off, that they wouldn't classify anything as a gorilla anymore, because typically such an issue couldn't be fixed just within a few hours after it appears in the news. because you would need to augment your data set, you would need to collect more data, retrain the model. It's typically something you wouldn't be able to do within a few hours very well. So I guess they just turned off the prediction of the gorilla labels as well as maybe some other unfortunate labels that could be misinterpreted. That was probably a quick fix, and then later they fixed it better by collecting a better data set, doing a better exploratory data analysis. So you see how class imbalance can impact an image classification. So given the tasks you're working on in your projects, think about it. Someone here writes in the chat that he's aware of some problem with self-driving cars not detecting people of color and children properly. Maybe the case too, simply because the training data was not representative. So you see, just collecting more data does not help. Collecting more representative data helps. And that's the tricky part. So just collecting more data is typically not that difficult. More representative data is more difficult and requires a way more sophisticated exploratory data analysis. There are other types of biases, and I want to look briefly with you into them. So, as we saw, the issue of class imbalance, there can be other types of biases. And another one that is quite common is covariate shift. Covariate shift refers to a different kind of bias. Concretely, where we say the training data and test data are distributed differently. Here with data, we don't mean the combination of X and Y, but what we mean is with data is the X, so the input data. And here we would assume for covariate shift that the training distribution of X and the test distribution of X are different, while the conditional distributions for training of Y given X is the same as the test distribution for Y given X. And for example, if we have a two-dimensional data set, so we just have two features like feature one and feature two, we would visualize the training and the test data. This is what, for example, a covariate shift could look like. So the data is spread out totally different in the training than in the test. Obviously, that's a simplified example because I just have two features, and this has nothing to do with the labels, by the way. So it's only about the X, and we have like feature one and feature two, and we would see the data is totally different spread out in the training than in the test data. And covariate shift is comes with these two assumptions, and we would calculate our weight again as before, where we say the probability of this appearing in the test distribution divided by the probability of appearing this in the training distribution. But as before, we have these joint probability distributions, but then we would just plug in our assumptions from before, and we would then this time have this joint distribution of X and Y just split up as Y given X times X. So we can do that as well with our probability law that we saw before. And then we assumed that the distribution of X in the test and training are different, but the conditional ones of Y given X, they are the same for testing and training, as we said here. And as they are the same, we can just cross them out and we would simplify calculating the weight like this. So this helps, and we can calculate the weight more easy than before. Yet in practice, this is still challenging because X could be high dimensional. While we got rid of the label in this calculation, it's still an issue. And if X has a lot of dimensions, we still suffer from the curse of dimensionality. And it gets better, but it's probably not solved yet, or it's still challenging if X has a lot of different entries. So this is something, for example, I worked on during my PhD time, and so my doctoral research, and I thought about how this could be approximated better. That was part of my PhD thesis, to calculate this weight more efficiently and yet approximate it still well. And despite the curse of dimensionality. And that's something that I proposed in my PhD thesis. And it helped with regards to various use cases. So we could calculate this weight faster and possibly approximate it still, or actually still approximate it well. Concretely, what did I do in my PhD thesis? I just briefly want to tell you about this. And then we'll come back to vision in a moment. So in my PhD thesis, I worked on the detection of electricity theft. So electricity theft is an issue all over the world, in particular in emerging markets. And if you look into countries like India, Brazil, Nigeria, Pakistan, sometimes in some of these countries, up to 40% of the electricity distributed gets stolen. So what people do is they manipulate meters, they manipulate transformers and other infrastructure, always with the goal of getting electricity for free so it doesn't get recorded by a meter. And this was my PhD topic. And there I came across the issue of biases in the data set. So we had biases in the labels because I said 40% of the electricity may get stolen, or the 40% of the electricity distributed. However, that does not mean that 40% of the customers steal. It's far less than 40% of the customers. So say now maybe 10% of the customers steal, just as an estimate. Then we have a big class imbalance in the data set. That was one of the issues, but the other issue was the covariate shift that I just talked about. And for example, where a covariate shift could appear is this scenario here. Imagine for now, it's simplified, but it helps us to understand this issue. Imagine you have this is like a state in Brazil, and we have for now, in this simplified example, we only have two cities. We have a big city, which is denoted by this big black circle, and we have a small city denoted by the small circle here. And we have obviously way more customers in the big city than in the small city, and we can carry out a certain number of inspections. So we have a certain number of technicians, we can send them out for a month and say we have most of our technicians in the small city and not that many technicians in the big city. So we carry out most of the inspections in the small city, and this creates a bias. Why does it create a bias? Because the electricity consumption in the small city is totally different than in the big city. Because in the big city, so this is in Brazil next to the shore, here it may be very hot both in the summer as well as in the winter. So there's a lot of electricity consumption for aircon. While more towards into the country, it's maybe very hot in the summer, but a little bit colder in the winter. Still warm compared to Germany, obviously, but maybe less air conditioning is needed. So the consumption behavior of the customers is different. Yet we carry out most of the inspections here and not in the big city, so that would create a bias because the behavior is different, and we carry out most of the inspections in the smaller city and not in the big city. Maybe just confirm whether you see that this can lead to a bias. So thumbs up is you got the example. And this is a example of a covariate shift. In practice, obviously, the issue of covariate shift is way more complex. So it's not just an XY coordinate, it can be way more because we have obviously many more cities, but still we could say XY coordinate. But there are other things that differ among the customers, not just their location. Maybe the type of customer, is it industrial or private home? Is what type of meter do the customers have? Maybe some meters can be manipulated more easily than others, and much more information. So we actually have a high dimensional covariate shift here. And for that, calculating the weight like this is still difficult. Still better than this one here, but not perfect yet. So we may have to come up with some new methods, and that's what I proposed in my PhD thesis. Now, how does this relate to computer vision? Say you could have a covariate shift if you have in your, say, training data more bright images and in your test data more dark images. So it's sort of your images in the training data tend to be more bright, while in the test data they tend to be more dark, for example. That could be one covariate shift. We're not talking about the labels, obviously. Or if you have other properties, say you want to recognize people in an image, and in your training data, you tend to have just a few people in an image, while in your test data, you tend to have way more people in it. Because, say, you have your training data, you somehow took these images, and then when you apply the system in the wild, so in the real world, you have way more objects and people in the images. And then you have a covariate shift, and your model may not work as well as you expected before. And there can be many, many more causes of covariate shift in computer vision. And it's something you need to think about also, maybe for the Cronus challenge, maybe for your regular projects, if there's a covariate shift or not. Measuring covariate shift, however, is way more complex than measuring class imbalance. So class imbalance can be measured quite easy because you just count the number of labels per class in your training set, in your test set. So it's a very easy operation to calculate or determine if there's a class imbalance. Determining a covariate shift, in fact, is not that easy. And multiple methods have been proposed. I also came up with some of this stuff. And if you're curious about learning more about biases in data sets, I wrote a paper during my PhD time, which was then also part of my PhD thesis, and it's called Impact of Biases in Big Data, and which was a survey paper, and I surveyed what other did, plus came up with some examples of my own, and some of this appeared later also in my PhD thesis. And in there, I also present some methods how we could actually measure a covariate shift if we wish. But determining covariate shift is more difficult. So first of all, before you try to reduce your bias, you need to measure whether there's a bias. And for the covariate shift, this is more tricky. It's been 8 years since 2018. Obviously, other people have published on this stuff since then, but these theoretical foundations haven't really changed. And I personally feel the issue of biases is still underrepresented in the literature. And in machine learning courses, professors talk about how to train models, but they don't talk too much about how to measure and remove biases. And class imbalance is probably the easiest bias, and there are many other types of biases which are less obvious than the class imbalance. Now, after the break, we will look more into uncertainty in learning. And what we want is we want to build better we want to make better predictions. So we want to build better hypotheses, so better models that make better predictions. Biases are one of those issues, but they can be much more around uncertainty in learning. And how do we actually assess a learner or a hypothesis? What we can do is we obviously have training, validation, and test sets. So we train on a subset, we want to test on a different subset later, and oftentimes we have a validation set in between, for example, to do model selection and other things. And eventually, the model we have finally picked, we would apply the test set to. We can evaluate hypothesis by calculating a confusion matrix, for example, and from the confusion matrix, we can calculate different measures, different metrics, like accuracy, F1, precision, recall, area under the receiver operating curve. For regression models, we have the R-squared metric and many more. We can even do cross-validation to get a better estimate, but there are challenges. Whatever we try here, there's class imbalance, other biases, and so forth. And all of these approaches here are helpful and we need to do them, but they are not enough. When we evaluate hypotheses, we can come up with a couple of more advanced questions. For example, we have an observed accuracy of a hypothesis over a limited sample of data, and we want to know how well would this actually estimate its accuracy over additional examples. So we have a limited sample, maybe very limited sample of data. We can estimate the accuracy, and yeah, can we estimate what the accuracy would be if we have additional examples? We could also see that we train multiple models, and one model outperforms over some sample of the data, but so it outperforms a different one on some data set. But how likely is it that this hypothesis, so this model, is actually more accurate in general, not just in one data set, but in other data sets as well? Or if the data is limited, what is the best way to use this data to both learn a hypothesis as well as estimate the accuracy? All of these questions are relevant to machine learning in general, not just to computer vision. And we can address these questions with different methods. Maybe for some of them, confidence intervals could be helpful. Maybe for some of these other questions, for example, question 2, we could also think about statistical tests. In particular, we could choose a paired two-sample t-test. So you've learned about statistical tests in your statistics class, and there are lots of statistical tests out there, probably hundreds, and there's one that is the paired two-sample t-test that could maybe help us to address the second question. Now, we could actually spend the whole semester just on uncertainty in learning or make a separate course about this. Today, it's just in the selected topics towards the end of the course. And these questions, so I'm curious, do you feel that these 3 questions have been addressed a lot in your studies so far or in the literature you read? If you feel you have learned a lot about this so far, maybe send me a thumbs up. If you feel that these questions are maybe haven't been discussed that much yet, maybe send a thumbs down, and I'll just see how many thumbs up and thumbs down we'll get today. So I'd like to see some reactions from you. If you feel these 3 questions have been answered a lot in your studies so far, or in the literature that you read, thumbs up. If you feel you haven't seen too much about this yet, thumbs down. And I see a majority for thumbs down. So some people feel they have seen a lot about this. I think these questions are often not too well addressed in a lot of the literature. Obviously, this stuff here is addressed a lot also in introductory courses and in literature, but this here probably not too much. And when I created those slides in the past for the big data course, obviously, I could create 50 slides on this, but it turns out these questions have been answered extremely well in a book. And that book is from Mitchell, and the book is simply called Machine Learning, and the book was published in the late 90s. Obviously, what the book does not cover advances in deep learning since 97. I think there's a little bit about neural networks in that book. And yeah, there's actually some stuff about neural networks, how you can calculate the partial derivatives by hand. And the book obviously is now almost 30 years old, and recent advances in deep learning are not addressed in it. But it's still a very good text on machine learning and fundamental questions in machine learning. And how to address these three questions from before. There's a very good book chapter, it's like 26 pages, and it's called Evaluating Hypotheses. And it shows all the stuff with the confidence intervals, the statistical tests, and so forth to answer these three questions. And because that book chapter addresses this so well, I'm not creating a lot of separate slides here, but I rather would, if you're curious, to answer these three questions, I would advise you just to read the book chapter. It's obviously sort of more an advanced topic, but it can help you to build better machine learning models, which you could use in this course or somewhere else. And it may help you to set yourself apart from other graduates who don't know this kind of stuff, or other students who don't know this stuff, because just training some model, a lot of people know now, but how to build them more reliably, a lot of people don't, and probably even a lot of AI professors don't know. So I would advise you to read this book chapter, and it will answer those three questions very well for you. Um, when it comes to uncertainty in learning, there are lots of different approaches that could help us with this. One is, for example, a so-called Gaussian process. And the Gaussian process is a non-parametric supervised learning method that can be used to solve regression and classification problems. And these Gaussian processes, they will not just make a prediction, but rather they will show us a little bit more. For example, for a regression problem, you need to bear in mind the following. Or when you have a regression problem, usually, or no, not usually, let's start, the usually will come in the next few sentences. When you have a regression problem, your labels are from a continuous interval. And usually, every prediction you make is somewhat wrong. It will probably never really be fully correct. In a classification problem, you have a finite number of possible label values. So there are a lot of predictions that you make. If you do it well, they would be correct. But with a regression, typically most of your predictions would be, or nearly all of them, or all of them would be somewhat off from the reality, because you have a continuous label, or the value of your label is continuous. So you're always somewhat wrong, and the Gaussian process could help you to address this. So what we see here is an image from the scikit-learn website, and what we see is we have observations which are in blue, and we actually have an underlying function which is this blue dotted line, which is some sign, and we see where it goes, and we have observations. So they are sort of a bit off from the original function because of some noise, and we try to do a prediction. And what we see here is a mean prediction. So we try to predict and then interpolate sort of the mean. And this is this orange line. And what we see is where it's a mean prediction, we're a bit off from some of the examples, but probably we can estimate the true underlying signal sometimes quite okay, I think, at least for this limited amount of data. Yet, our predictions are wrong. And what we care about is how good or how bad are the predictions. And what is actually more interesting is something like a confidence interval, where we want to have a 95% confidence interval. And we want to visualize this in orange here as well, as you can see. And this is something that works surprisingly well with a Gaussian process, which not only makes a prediction, but it can also predict us this confidence interval. And we see, for example, in this range here, we are quite okay, but over here, well, the true signal is just at the very end of the confidence interval. So actually here the predictions don't work very well. It's still within the interval, but just at the edge. Over here, we don't have much data, so obviously we see we can't estimate the confidence interval very well. But once we have a few observations, we can. Has any of you ever used something like a Gaussian process on data? If you have, maybe thumbs up or thumbs down in case you have not. It's one of different approaches, but you can use it for regression. You can use it also for classification. What I told you here about the definition is this one on Wikipedia. It gives an okay definition, but a somewhat longer one. So feel free to read this on your own in case you wish. But I just wanted to show you what the idea of such a Gaussian process is. So it can also quantify its confidence in the predictions. Something you could also use in for classification, or if you build a regression system, obviously you can use it for regression, and the system can quantify its confidence. And that's something quite helpful when you make decisions under uncertainty. Maybe this can help you sort of for debugging to understand how confident the system is in its predictions. Maybe this can help you also to find a bias in the data and or maybe an issue in your data quality to address. So overall, a very helpful method. There are some people, they are very fanatic about Gaussian processes, and to me, it's one of many tools. For some problems, it's helpful. For others, it's not that helpful. And for this, we need to look a little bit into advantages and disadvantages, because what I don't like is sort of some people, they are like fanatic about certain methods, like a religion, while others totally object these methods. And rarely it's that white and black, but rather we need to look at when these methods are helpful and when they are not that helpful. So a Gaussian process can give us reliable estimates of their own uncertainty. So this is cool. And we could even incorporate expert knowledge with some tricks. So that can be done too. But the Gaussian processes have some disadvantages too, because they are quite computationally expensive. And I said before that Gaussian processes are non-parametric. Who of you knows the difference between parametric and non-parametric models? If you know this, maybe thumbs up. If you don't know this distinction, maybe a thumbs down. I just want to see if anyone has come across this terminology. So only thumbs down. So obviously, non-parametric, I think, is a really bad term because it creates sort of the impression that these models would not have any parameters, and that's wrong. So I'll start with parametric models. A parametric model would be, for example, a neural network, at least a regular neural network, or a linear regression, logistic regression. They are all parametric models because the number of parameters or weights in the statistical model is fixed. So you have a fixed number based on the architecture and your data, say that the length or the length of the input vector. And then you would have a certain number of parameters or based on the number of hidden layers in your neural network. And a non-parametric model still has parameters, but the size is not fixed. It depends on your data. For example, those of you who know a support vector machine, a support vector machine is also non-parametric because what we care about are the support vectors. So a certain typically small subsection of the training data, those would be the support vectors to span up the decision boundary. But the number of support vectors is not fixed. It depends on the data. So the number of parameters on the model depend on the exact data and not just of the size of the data. So that's what non-parametric means. You still have parameters, but the number of parameters is subject to the exact data. And so these Gaussian processes, they are non-parametric, and typically these Gaussian processes, they need to take into account the whole data each time when they make a prediction. So they are unfortunately relatively slow, and in high dimensional data, they don't work too well. Typically, the Gaussian processes only work for a few dozens of dimensions, but in a lot of real world data, we have way more than just a few dozens of entries in the vector. So then this doesn't work very well. But for some problems, the Gaussian processes can be helpful. So for others, not. Maybe it's one of many tools in your toolkit that you use in the future. There are newer approaches that have become very popular in the last few years, in particular to address the issue of uncertainty in learning. And that one that I'll show you now is called conformal prediction. Conformal prediction is, first of all, a highly generic approach, and it can help us to quantify our certainty or uncertainty, whatever way you see this, when we do classification and regression. And for that, I will also switch to my iPad and I'll show you briefly what the methodology of conformal prediction is. And then we'll see why this has become so popular in recent years. So conformal prediction. And that topic could again be very helpful for your projects to build more reliable systems. And it could also help you maybe to win the Cronus challenge if you look in. So it's not a guarantee, but probably the teams that investigate conformal prediction in the Cronus challenge, plus biases and all the other stuff, they will certainly have probably an advantage. But you'll see that. And I'm curious also which methodology will win the challenge at the end. So what is conformal prediction? Conformal prediction is actually a relatively easy approach from the methodology, but it was only became popular in recent years, and the research largely goes back to the last 20 or 30 years, and it's a method that has become now more popular. What it allows us is we want to create, and everything I'm saying is also in the slides, but we'll develop a couple of formula now. We want to create prediction intervals or prediction sets. And what we have is guaranteed guaranteed frequentist coverage probability. So I'll write this down. Guaranteed frequentist coverage probability. As you know, in statistics, there are these two worlds, frequentist and Bayesian statistics. Again, oftentimes like a religious approach. Some people only believe in frequentist approaches, while others only believe in Bayesian approaches. I've never really been like this, that it's on either the one or the other world. I think both worlds have their pros and cons. But it's sometimes like a religious battle whether you should belong to the frequentist or the Bayesian world. And this conformal prediction here gives us guaranteed frequentist coverage probability. And the interesting thing is this is for any or from any predictive method that works the following, that we actually have a probability of the label given the data. And actually, a lot of predictive methods do exactly this, that we use in machine learning, that we want to infer a probability of a label given the input data. And this conformal prediction approach will give us these prediction intervals or sets with guaranteed frequentist coverage probability from any predictive method that works this way. There are other predictive methods that don't work this way, but many do. And the interesting thing is that this conformal prediction sort of can be plugged in, we will later see this, into a lot of machine learning models that you know already. So you don't need new libraries, you don't need totally new models. Rather, we can augment our existing models with a layer on top for the uncertainty quantification. So the goal is that we want to have an uncertainty quantification. And all I'm writing is also available in the slides, so you'll see this later. And what is key to this is distribution free. Because a lot of statistical methods, also a lot of machine learning models, what they assume is that your data comes from a certain distribution. I don't know if you heard this already, but a lot of machine learning models assume that, for example, your data that you use comes from a Gaussian distribution. Or maybe not the data, but say at least the errors would come from a Gaussian distribution. Are you aware of this? That a lot of machine learning models assume this. Maybe thumbs up or thumbs down. And some models don't necessarily assume the Gaussian distribution, but say something from a more abstract perspective, the so-called exponential family, which is a class of distributions where the Gaussian distribution falls in. But I've seen a lot of thumbs up so that you're aware of this. And the good thing here is some people argue, well, all this stuff, assuming always the Gaussian or something from the exponential family, this is all 20th century, outdated, and now new statistics is distribution free, and we should only use distribution free stuff. Again, I oppose this because I think the assumption about the Gaussian distribution or the exponential family probably makes a lot of sense for a lot of problems, not for all problems, and sometimes people I don't know, try to convert their data so that it falls into the hopeful distribution. Also, that one is probably not too smart and sometimes really the wrong choice. But just because there's now some new methods that can help us to work with distribution free, does not mean we need to kick out all the past methods. And yet, it's again a tool I want to show you, but this distribution free, obviously, there has been more research on this in statistics in the last few years, or probably last 10 or 15 years. And if we have that, obviously it's cool because then we probably can apply this to a much wider range of data sets and get more reliable results than before. But we only assume one thing actually with our conformal prediction. What the only thing that is expected or required by conformal prediction is the so-called exchange ability of data. And exchangeability means if we have our data set, we could just change the order of the examples. So we have examples 1, 2, 3, and so forth, and we could just shuffle this, and we would assume that that would not have any major impact. So conformal prediction in its purest form could not be applied to time series data, because in a time series, we don't assume exchangeability, but there are even extensions of conformal prediction to time series data. But that's something we will leave out for now. So that's the idea of conformal prediction. Before I develop the formula, everything I've just said is available in this slide. I just wanted to develop this briefly with you. And what I'm showing you now for the remainder of this lecture is something that comes from the Murphy book. So the Murphy book is a famous machine learning book, and it was for a long time one book. And then a few years ago, the book got split into two books, and both got extended. And the second one is then the Advanced Topics book. So the two books combined cover more topics than the original one Murphy book. I have not studied the Murphy book too much. Other people, they've studied it more, but it's just one of different, I think, philosophies in the textbooks in machine learning. But the Murphy book still has some interesting aspects in it. And the second one, then the Advanced Topics, covers at least a little bit uncertainty in learning, and in particular then conformal prediction. And what I'm showing you is just an essence of what the book actually says about conformal prediction. So I've put the reference here. And with that, I can switch back to my iPad. We'll develop a couple of formula now and see what makes our conformal prediction so interesting. So conformal prediction says that we would need some heuristic notion of uncertainty. So we need some heuristic notion of uncertainty. Depending on your exact problem, for example, if you do classification, this could be the softmax score. I'll show you this in a moment, what the softmax score does. If it's a regression problem, for example, that notion of uncertainty could be the variance, for example, and we will use this to define a conformal score. And a conformal score we would denote by S of X and Y, and this will be a real number, and it measures how badly the output Y conforms to X. So we could also call this conformal score rather a non-conformity score, because we say how badly the output conforms to X. So large values of the score are less likely. So we could rather think about this as a non-conformity score. Who of you knows so we want the conformal score. Who of you knows the softmax function? Who has heard about softmax? I don't know if I mentioned softmax actually when we did neural networks, but if you heard about softmax, maybe thumbs up or thumbs down. So one, two people know it. Can you tell us what softmax is? Maybe turn on your mic or yeah, maybe turn on your mic because it will probably take too long in the chat to describe what softmax does. Is anyone brave enough? Turn on mic and tell us.
Yeah, it basically converts the continuous like machine learning kind of outputs to the something resembling probability distribution, at least in terms of like rigid limitations of probabilities, like where values are between 0 and 1 and sum up to 1.
Yeah, so we have multiple values and we just want them to sum up to 1 eventually to have a probability distribution, right? That's what you said.
Yeah.
Yeah. So where you would need a softmax, so just an excursus softmax would be, say you have a neural network and in a neural network you have multiple output units, and each of them, so this is the output layer, they each gives an output value, and finally you just want to make sure that these outputs they add up to 1, and that obviously the largest output would get even more amplified within that distribution. And for that we can calculate the softmax score. So something that we would do is, so softmax score could be denoted here by a sigma. I pass in a vector Z. Well, I'll just write this better. And I pass in a vector Z, and its element I would be converted from its value to the following. So I take the exponential function and raise it to the power of Zi, because we care about that ith index for now, so the ith element in that vector. And we would raise e to the power of zi. So just put in the set like this, then it's correct. And I would divide this by a sum where I have an index j from 1 to k. So I have k many entries in my vector z. And I would take then that value zj and raise e to that power, and I add up all these e's and divide by that. So this is the softmax definition, and then I would apply this softmax function to every entry in Z, and eventually I would have guaranteed that the entries in the new Z they add up to 1, and that the big components they get amplified and the low ones would be even more diminished. And yeah, you could use this for a neural network, for the output layer, plus probably many other applications in signal processing and machine learning. So we could use the softmax function for classification as our notion of uncertainty. In regression, we could use variance, and we could use this in some way, as you will see later, to define our conformal score. So what do we do now? How we calculate this conformal score exactly depends on the data and the use case, and there are lots of ways we can do this. We will see this later for classification. But now assume we know how to calculate this conformal score S, and I'll just highlight this here as well, of the input and the label, and it will be a real value. What I can do now is I can next calculate a so-called calibration set. So calculate a calibration set of our M labeled examples. And that we did not use to train our hypothesis. So I'll probably add this. So we calculate the calibration set of M labeled examples that was not used to train our model F. And then we wonder how can we calculate this set. I'll show you this. So S is the calibration set, and it stores the entries SI for our M example. So M here does not mean the training set, but we have M labeled examples, and that was not used to train F. And these conformal scores are then SI, where S is of the input XI and the corresponding label. And we calculate the set for I from 1 to M. So we do this for all these M examples. Now, we would specify a desired confidence threshold. And this confidence threshold is called alpha. For example, alpha depends on your use case, but we say now it could be, for example, 0.1. Then we would compute the 1 minus alpha quantile Q hat of S. Remember, S was this calibration set, and we want to calculate now, for example, if alpha is 0.1, we would calculate here the 90% quantile Q hat of our S. And what we want to do next is, if we have a new test input, we want to compute the prediction set. And we'll soon see why this is all relevant for vision. So say we have a new test input. That is called X of M plus 1. So one more that was not used of this calibration set. Now probably underscore in red the calibration set. And what we want to calculate now is for this new test input, we compute the so-called prediction set. Prediction set is, we mentioned this before, because that's the goal of what we want to get out of our conformal prediction, and soon we'll visualize it. So we have the prediction set, and that one is often denoted as T. So the prediction set of our test example, that one we would define the following. So what we want is we want all the outputs y, so all the possible labels that are plausible given the input. Because also when I make a classification, the label could be wrong. And what I want in this prediction set is to have the labels that are plausible given the input. We could do this for classification, but the formula I'll show you now works exactly the same for regression. While for regression, we would then have an interval and not just a finite number of labels. So we want the labels y for which this conformal score for our example here and its label is less than or equal to our Q hat. And remember that Q hat was this 1 minus alpha Q quantile. What the book writes is, just as a quick note for this threshold, the book says that the user would specify this confidence threshold. The user here does not mean end user sitting in front of a computer. User in the book would mean the data scientist that builds that AI. That's the one who would specify the confidence threshold, depending on your use case, obviously. But user in the book, and I think I also used the word user in the slides because I was inspired by the book. This does not mean end user, it's the data scientist. So, and what we have is the prediction set, and intuitively, this prediction set would be all the plausible or all the outputs y, all the possible labels that are plausible given the input. And the input was that one here. And we have all the labels here y that we go through, and we take the ones for which this conformal score of the example and the label are less than or equal to Q hat. This one I will show you now in the slides. In the slides, it's obviously all well formatted for you. And this is what we just went through. Just one note that is also made in the book. We can calculate the 1 minus alpha Q-tile in actually a better way. 1 minus alpha could be replaced by this formula to account for the finite size, but it's just a tweak. For now, we just stick with 1 minus alpha. And so what does such a prediction set look like? What you see here is, say, for a regression problem, what we get is a quantile regression. So the prediction set is in here, and this would be all the plausible or the plausible range or possible or plausible interval of where the label value would be in. So this given for our confidence threshold that we defined. So this looks a little bit like what the Gaussian process did, but actually this here works different because the Gaussian process works internally different. It doesn't work with this prediction set, but it's a quantification of the certainty based on the confidence threshold I said before. And that goal is the same of the Gaussian process as well as here the conformal prediction. Yet internally, this works totally different. And here compared to the Gaussian process, this actually runs much faster, plus it's distribution free. So it's a huge advantage compared to the Gaussian process. And also, if we have a classification problem, say we have an image and there could be lots of different animals in it, or we want to classify the image based on the animal. We have a lot of different possible classes. The prediction set would be what we have here is we have a cumulative softmax output. So cumulative means this one here for fox squirrel is the largest output from the softmax function. then what we see here is the delta to Cray Fox and even a smaller delta from Cray Fox to Bucket and then from Bucket to Rain Barrel. So it's not just animals, possibly, it's other classes as well. But what we see here is not the softmax output, but the cumulative one. So we start with the largest one and we go up to the threshold, Q hat that we defined. There are a few more notes in the slides about some inequality, but I'll skip this for now. If you're curious, you can read this at home or in the book. There's a better or an additional justification why this 1 minus alpha is actually helpful to compute. And what we need is the true distribution of the data. So this is sort of a justification why this conformal prediction makes sense as a method, but I'll leave this up to you to read this either here or in the book. And a little bit more text. We can apply conformal prediction very easily to classification. For example, the conformal score could be just calculated as 1 minus the prediction. So large values are considered less likely than small ones. That's exactly what we wanted for the conformal score. So for classification, very easily, we have the softmax score and 1 minus the softmax. That would be then the conformal score. What does this look like? Say we have, let's start with the simplest image in this example. We have this fox squirrel. We classify the whole image and we get a fox squirrel 0.99 prediction by the softmax score. And the way we set our confidence threshold, we only get one class in our prediction set. If we take more complex images like this one here, fox squirrel, and fox squirrel is in green because it's the right prediction or the ground truth, we have a softmax score of 0.82, yet for the threshold we set, so the confidence threshold, we would get 3 other classes like Cray Fox, Bucket, and Rain Barrel that are still in the prediction set. And if we take this image here, where the fox squirrel is not fully visible, fox squirrel is still the ground truth because it's in green, but actually marmot has a higher softmax score and therefore also appears in the prediction set. And there are a couple of other classes that appear in the prediction set. So this is one example of how we can apply conformal prediction to a computer vision problem. The good thing is conformal prediction is highly generic. We can apply it to lots of other machine learning problems. And what it allows us to do is we can quantify the uncertainty of the model. And what we need to define is based on our use case, the confidence threshold. And then we could use such an approach maybe for a multi-class output. We could use it for debugging as well. Sometimes this may help you also to identify maybe wrong labels in your data. So for example, in the training data, or it could be a sign that you may have to rethink class balance and address the imbalance. So this conformal prediction approach is very helpful to potentially predict multiple labels, can help you for debugging, identify a bias, and a couple of other things. So it's maybe one approach you want to be using as well in your project, either for a regular project to build a more reliable vision system. You could use this for the Cronus challenge as well. And the good thing is you don't need to implement this from scratch. There's a library called here the Model Agnostic Prediction Interval Estimator. And this library implements conformal prediction for you, so you can calculate your prediction sets. It can help you to control risks of more complex tasks like multi-label classification, segmentic segmentation in computer vision, and a couple of other things. So it's a very helpful library that comes with a lot of interesting features. And the good thing is you can wrap any model with it as long as it fulfills this requirement that we predict the label given X, and it must be scikit-learn compatible wrapper. But if you use scikit-learn, TensorFlow, PyTorch, or others, they are all scikit-learn compatible wrappers, and you can very easily, for example, use this library for a classifier. You have your classifier here. This could be like a Keras, TensorFlow, PyTorch, scikit-learn model, and you can just plug it into here, into your conformal prediction model. So that's something you can use very easy. The library comes with a couple of other interesting features. So I advise you to look into this, and you can use it for vision, and you can use it for lots of other stuff. Now, in addition to conformal prediction, there are a couple of other things that turn out to be or that turn out to have become more important in recent years. For example, calibration of machine learning models. I'll briefly mention what calibration is. So, say in binary calibration, the goal of binary calibration is to transform a score that some machine learning model makes that is not a probability to turn it into a probability. Because not all machine learning models actually give us probabilities. They give us some score, and we could turn that score that is not a probability into a probability. And these calibration algorithms help us to do this. And so the algorithms that are used for calibration, they can be interpreted as estimators of the confidence level. So they need the independent and dependent variables to be fitted. And what I have here is, so this also comes from the same library, MAPI, that implements conformal prediction. It also offers some work around binary calibration. What we have here is in Plu, we would have in Plu the output of a machine learning model that is not calibrated. And what we see here is we have in one dimension the accuracy, and in the other axis we have the confidence score. And this figure illustrates what we would get if we apply calibration. So if we calibrate models, we would actually want a situation where these scores are that we predict they are much closer to the true probability compared to the original output. Because what we see here, that these blue dots, they are quite off from this diagonal. But if we calibrate the model, we see in orange, we would have calibrated scores, and they would be on that diagonal. And this is something we would very much prefer because when we calibrate, the scores that we predict, they would be much closer to the true probability compared to the original output. And there has been a lot of research in recent years published on calibration. For example, it's been noticed that a lot of new deep learning models, they may be very accurate, but they are poorly calibrated. So they predict well, but they are not that confident in what they predict. And this has been shown in research in the last 10 years that a lot of these new deep learning models are often poorly calibrated. Now, you think, well, we could calibrate them with the right algorithms, and then we're happy, but this may lead to new unintended consequences. And for example, it's been shown through some work, if we try to calibrate neural networks or certain models, there could be unintended consequences. So if we calibrate certain deep learning models, we calibrate them, but actually we will diminish their refinement. And what is refinement? Refinement refers to the fact that when we have binary classification tasks, that we can still distinguish. And in terms of trust, we would see that this is an ability to differentiate between correct and incorrect predictions based on the predicted confidence. Usually, I don't put LinkedIn posts in my lecture slides, but there's Valeri, and Valeri, he's very famous on LinkedIn, and he posts a lot about conformal prediction. He posts a lot about calibration and trust in machine learning. And I follow him. If you're on LinkedIn, I can recommend you to follow him and follow his posts. I feel he's very much in this frequentist world. I've told you my view on this. It's helpful, but for other points, maybe Bayesian is still helpful. But follow his posts. I'm sure you'll learn a lot of new stuff. And that's why what he noticed here, or he came across some works and summarized quite well, that just enhancing calibration can lead to new unintended consequences. We're coming now close to the end of the uncertainty in learning subchapter. So far, we've seen biases in the data. We've seen conformal prediction, we've seen Gaussian processes, now calibration. But something we have always relied on is the ground truth in our labels. We assume the labels to be correct in the training data, but there is noise in labels as well. The labels in the training and the test data can be wrong. And over the last decade, some works have also been published on how we can learn from noisy labels. And there have been quite a few interesting studies in the recent years that have been published on this. And maybe that's also interesting for you. I don't know. In the data you're using, some of the labels may be wrong. For example, we talked about ImageNet. Who of you remembers ImageNet from when I talked about convolutional neural networks? Maybe just raise your hand or so if you remember the ImageNet data set. We talked about ImageNet when we looked at the AlexNet, at ResNet, and a couple of other neural networks, and said this is a reference data set. But some research has shown that quite a few percent of the labels in ImageNet in various versions are wrong. So noise in the labels is the reality, and so we need to address this as well through adequate methods. And this is something that has been studied in various papers, and here it's a very good survey paper on that topic from a few years ago that addresses the issue of noise as labels as well and looks at some common data sets like this one here. There's also been quite a few news on the internet in the recent years that a few percent of the labels in ImageNet are probably wrong, but it's millions of images, so double checking and agreeing on the right label, it's a lot of work. That's why if there's just a neural network that got a slightly better percentage than before on ImageNet, maybe that doesn't mean anything because maybe your data set is biased, maybe the labels are noisy, so and lots of other stuff may have gone wrong. So bear all of this in mind. When you work with the Cronus data set in the Cronus challenge, you can think about noise in the labels there. I think they spent a lot of time on reducing noise in the labels, but maybe you find something in your exploratory data analysis, and you find some noise there as well. I don't know how much noise is left. There's always some noise, obviously, and don't think they got fully rid of it. But maybe there's something interesting to investigate as well, and all of this could help you to build an even better classifier. So, this was the lecture part of the computer vision course. And I just want to briefly probably go back to the beginning of the chapter just to show you the big picture of what we did. So I'm just going back to the list of contents, which was here. So in this course, we started with an introduction. We saw why computer vision is so challenging. We saw pixels and filters, so very low-level operations, which we still need. I mean, if you have a very noisy image, maybe you first need to blur it a little bit to get rid of some noise, because if you don't blur the image, maybe there's just the noise will just affect your learning later on. So we still need these low-level operations. We've seen how we can identify regions of images and segmentation. We've seen machine learning approaches. We've seen classical approaches like histograms. And then we want to make it to object recognition. We want to detect, recognize, locate objects. For this, we typically need features. So we've seen different feature detectors like Harris corner detector or the Huff transform. And we can plug those features into different methods, more classic methods, more machine learning methods, and then neural networks, and in particular convolutional neural networks, they aim at learning these features on their own, plus the actual task. Neural networks are meant for that, and convolutional neural networks are helpful with regards to image problems. But you can also apply convolutional neural networks, for example, to text data. All of this was static data, and then we've seen how we can address image sequences, so videos, how we can track objects, how we can predict things. We can put in features, for example, into a Kalman filter. There are other approaches like the optical flow that we have seen. There are also neural networks that deal with time series, but that's something you will see in your deep learning course. You can use such approaches also for images or image sequences if you wish. But the Kalman filter we saw runs extremely fast because these neural networks, especially very large ones, are computationally quite heavy. Kalman filter is not and can be applied to so much more than just vision. So what I wanted was to provide you with a toolbox, more classic methods, more modern methods, and just because there's a new neural network, that doesn't mean that it's better than everything else before. You need to know the right toolkit and then pick the methods from the toolkit based on your task, because sometimes you may just have limited data, you may have limited computing resources, and subject to that, you need to pick the right methods. And then in the selected topics today, we saw biases in data sets and uncertainty in learning. And last year, the vision transformers were very popular for the projects. So we discussed that more in the lecture. This year, a lot of students are doing the classification challenge from Cronus. So if you want to learn more about vision transformers, you can watch last year's recordings or some other resources. And here in the selected topics, next year, there will be new topics. And just jumping to the last slide. So for the remainder of the term, you will focus on your projects. And if you have any questions on the projects, you would let me know. And we'll have these 2 guest lectures. I'll provide more updates about them in the coming weeks. And I teach other courses here as well. So if you're a regular student in Deggendorf in one of these AI programs, if you're an undergrad student, you have attended my algorithms and data structures course last year, now this year, computer vision. In the 6th semester, there's an AI project. It's a bigger course where a group of students works on a bigger project together. This is supervised by 2 of my colleagues and me. We split the students. I see some names here, be it from exchange students or some selected students. They are doing the AI project this year with me or with someone else, because it's the 3 of us splitting the cohort into different projects. I also teach an elective on quantum computing, where you may see me again. So I teach AI project in the summer, and in the winter I teach quantum computing. And then for those of you doing the mandatory internship, which is part of the AI undergraduate program, a lot of students do this internship in the winter terms. And there are two internship accompanying courses in the winter, and I teach one of them, which is called Innovation Management for AI, where we look into why AI projects fail, often from a management perspective, and how we can make sure that AI projects succeed. So we look into different models of how AI projects can be done. We look into regulation. We look into hypes around AI, when AI is actually helpful. We see different models of how AI projects can be done, of how to address fears, emphasize opportunities. And all of that requires a deep technical understanding, which you get from the courses up to there. Maybe some of you wish to take the quantum computing elective with me in the winter. That one will be available. And there are obviously more AI courses, for example, in our AI bachelor's program. There's an AI seminar, there's a course on autonomous robotics, there's a big data course, a deep learning course, and many more. So there are plenty of more opportunities in the future to learn more AI. And if you have any comments or suggestions on the course, I'll be happy about them. There will be a course evaluation in a few weeks, I guess. I have not received the URL to the course evaluation yet, so I guess it's not been created by the administration yet. When the course evaluation is available, I will share those URLs with you, and I wish you all the best for your projects. Any questions on the projects, I'll be happy to help. So just get in touch, and I'll be happy to respond by email, video call, or we have a meeting on site. And I'll see you for the presentations at the end of the term. You know which date you're assigned to, you know the marking scheme, you know that you have to attend all the presentations on the day of your presentation. Don't be late, don't leave early. We've talked about all of this. And I'll see you probably two more times then for the guest lectures. And once that has been determined or once that has been organized, I will let you know. Are there any questions so far about the next steps in the course or any technical questions you may have? If so, maybe just raise your hand now, so I'll wait for you here in Zoom. And with there not being any questions, I wish you a great evening and all the best for your projects or the challenge, whatever you're working on. And I'm very happy a lot of teams have progressed with that challenge. And after the Q&A earlier today with Cronus, I guess we have some new input, plus the stuff today about uncertainty in learning and biases. You can build even better models. And I look forward to seeing your projects in a few weeks, and have a good evening, and bye-bye.